Hello once again, AP Calculus AB students. Mr. Record here. We are still taking a look at implicit differentiation. This is example 3 in my series. And we're considering a pretty well-known popular function, or a relation, I should say, that you may remember from perhaps a second year algebra or pre-calculus class. The equation x squared plus 4y squared equal 4. And we're actually going to do quite a few things with this in this video. Some things calculus related, some things algebra related. So let's get right down to it. In part A, it says that we want to sketch a graph of this relation on the coordinate plane provided. And I'd like to first approach this without using technology. And we'll talk a little bit about how you might be able to handle this if you had a graphing calculator. But the very first thing that it would be nice to be able to recognize is what kind of relation this is, which family of previously studied relations does this fit in. And then hopefully it does kind of strike you that this is indeed a conic section. So it would fit into one of the four: parabola, circle, ellipse, hyperbola. And upon a little bit more inspection, we hope to decide that this is indeed going to be the sketch of the ellipse conic section. But it may not quite be in the form that you were taught in a previous class, but that's a very easy fix because we just simply need to divide both sides by 4, and we would get this particular equation set equal to 1, which is a cornerstone of being able to successfully graph two of the popular conic sections, the ellipse and the hyperbola. Now, if you got to delve into this a little deeper, you'll find out that the center for this particular ellipse would be 0, 0. The HK value are both 0, as you can see. There is no other items with the x squared and the y squared. And in this particular problem, we then sort of begin to think about, well, what would be the amount that we would count out in the x and the y directions. And so I've kind of denoted that 2, the square root of 4, would be the amount that we would count out in the horizontal direction, and 1 will be the amounts that we would count out in the vertical direction, and those would be both taken from the center 0, 0. So when you go to the sketch here, you don't really have a lot of guidelines to sketch the graph of an ellipse. If you recall, you pretty much have to do this free-handed, and you basically have 4 points to go by, and we list them out here: two units either side of the center 0, 0, and then once again we'll go in 1 unit above and below. So it's these outer 4 points that just simply need to be connected. And notice I did delete that center. A lot of teachers may not make a big deal out of it, but the center is not part of the graph, so I don't like to kind of get it confused with anything that is sketched. So this is your ellipse. I always tell my students, try as best you can to not draw a diamond. You want to try to not also draw something that looks like an oval. Ellipses are not ovals. A lot of kids will draw footballs and lemons and things of that nature, but I try to get it to be a little bit as smooth as possible around those outer edges. So there's our sketch of the graph of the ellipse. In the box there, for those of you who do use a TI Inspire, you'll notice that there are 2 different methods that one could use to sketch this using technology. Method 1 is pretty foolproof. If you were to sketch any implicit equation, it does not have to be a conic. You would use the zeros command. Method 2 talks a little bit more about conics. Now, if we were to take a look at this on the TI Inspire and use one of the methods, let's take a look at the first method. Like I say, I like this one because it seems like it works for many conics. We'll type in the command zeros, which might seem a little strange. It's just basically some calculator syntax that just needs to be included. Zeros will turn to unitalicized once you put the S in. And notice that we're going to type in the expression x squared plus 4y squared minus 4, it says. So you basically want to bring that 4 from the right side over to the left side. And essentially you're going to have this particular equation set equal to 0, but you don't want to say equals 0 within the parentheses. Instead, as soon as you get to the last term that would be on the left side, we're going to place a comma, and then we put a y value, a y in. Again, don't read a lot into exactly what's going on. It would take a little bit longer to explain that than really what needs to be explained. And just know that for the TI Inspire, it does generally a pretty good job of sketching the graph. And like I said, this one's a pretty simple one. I think as soon as we hit enter here, we're going to have a pretty good depiction, hopefully, of our ellipse. Don't worry a whole lot about that F12. It's just a way that the calculator decides to sort of label it. And I went ahead and decided to put some grid lines over here so that you can a little bit more easily count the squares. So definitely method one, a great method to use to graph not just any type of conic section, but pretty much any implicitly written equation. There are a few exceptions, some of the more complicated ones, but we'll talk about those in a different video. Method two relies a little bit more, I should say I've underlined the coefficients of the current terms that are in the original equation. You would actually go into a completely different graphing menu in which to do that. It's the menu option that allows you to, once I get into a graphing page here, notice the F1 of X isn't going to do a good job with this. So I want to go into a completely different type of menu. F1 of X is reserved to graph functions or these very special implicit equations that we can use the zeros command on. So instead I'm going to use option 3, and I am looking at an equation here with option number 2. Notice the arrow, it's going to depict more options further, and once you get to this stage it's pretty clear ellipse is a choice, option number 4. Notice with the TI Inspire you can also just hit the buttons, so I would be menu 3, 2, and then, but I did not choose ellipse. The reason is because the equation wasn't written in standard form yet, not originally. Notice it was written in a form where you did not have the fractions, so I chose the equation, the last option there. And then I can just input the coefficients that I saw. Hopefully you remember from the last slide, x squared had a coefficient of 1. There was no xy term. That would just give you a sort of an obliquely oriented ellipse. The y squared was 4. I did not have an x term nor a y term, so I could make their coefficients 0. And then remember my last constant was a -4. So that since the plus is sort of built into this equation, it's going to be very important that you remember to put the negative in the 4. Hopefully those are entered correctly, and if I were to hit enter, I should see the same exact equation. And moreover, I actually get a nice label this time when you use this method. It's a great method. The only problem with it is that it's a little limited in that it truly is only going to graph members of your conic sections. Okay, now we move on to part B of this problem. I told you we were going to do a lot of things with this. And part B is where the calculus enters the picture. And we're going to take the derivative of this particular equation with respect to x. We're going to find dy dx. And obviously this is going to require an implicit differentiation approach. And as you may have noticed if you've watched some of my other videos, I always like to begin these problems by just writing some notation. A lot of times my students don't like this because they always say, hey, you haven't done anything in the first step. And while they might be right, it does at least set the stage to do the derivative correctly. And as you can see, when I get to this 4y squared, the derivative would become 8y times dy dx. That's where the implicit differentiation comes into play, because you're differentiating a y variable and not an x variable. On the right side, derivative of 4, of course, is 0. And this is going to be a very simple equation now to solve for dy dx. I'll subtract the 2x to the right, divide by the 8y, and then you can do a little simplification step here by reducing the -2/8 to get -x over 4y. And that's about as good looking as our implicit equation, or derivative rather, is going to get. It's very common to have both x's and y's in our result for our derivative. So we're going to remember this guy. This guy's going to kind of pop up later on, and we're going to use him, or at least revisit him in just a little bit. In fact, I will have to know what this particular derivative turned out to be in order to answer part C, which is just simply to find the slope of the tangent line to the curve at the point. If you're watching this video, you probably have done many kinds of problems like this in the past where you had to evaluate a derivative specifically at an ordered pair. The only difference now is that the derivative that you took was done in an implicit fashion, which meant that both the x and the y probably are going to be used now. I think before you just typically had the x variable that was going to be plugged in. So if you want to have some really good looking notation here, you could say that the derivative of y with respect to x such that we evaluate it at the ordered pair here, radical 2 comma negative 1 over radical 2 would equal, replace the x with radical 2, replace the y with negative 1 over radical 2. This is a bit of a mess, so definitely needs to be simplified. So in the denominator, 4 times negative 1 over radical 2 would simply be negative 4 over radical 2. And then really our last step here is just to take care of the division by multiplying by the reciprocal, radical 2 over negative 4. And we'll notice that the radical 2's multiply together, and they will make a positive 2. And the negatives canceling, of course, leaves a 4 only in the bottom, and we reduce to 1/2. And that would be the value of our derivative at that ordered pair, or more specifically, and more importantly, that would be the slope of our tangent line that we could draw at that particular ordered pair. Now, if you look back here, it's kind of nice sometimes to know, is our answer making sense? Does it seem like it would be legitimate? Well, you could locate the ordered pair somewhere on this coordinate system. Of course, radical 2 is a little bit tough to kind of reason out where it is. So I always tell my kids, yeah, it's approximately 1.4 in a pinch. So marking that on the x-axis right there. Now, negative 1 over radical 2, the y value in that coordinate might be a little tougher to figure out. You could certainly use a calculator, I suppose, here if you wanted to figure that this is going to be some kind of a decimal. But you could also rationalize it if you had to. The whole idea of rationalizing a denominator was sort of brought forth because it made these calculations a little easier. So if you took 1.4 and divided by 2, you're going to get, of course, 0.7, and the negative just kind of pops in there. So it's pretty easy to find that negative 0.7 there would give us an ordered pair in that fourth quadrant here, and then the line tangent would look something like that. And I think it's at least fathomable that the slope of that line could conceivably be 1/2. I don't think I drew it in perfectly, but at least it's the right sign. It is a positive slope. So that does take us to part D, where we write the equation of the tangent line drawn to the curve at that same point. And if you recall, our slope was 1/2. We're going to remember part C. And the rest of this part is pretty easy. You're just dealing with a formula from Algebra 1 class, the point slope form that says take y minus the y1 value, set that equal to the slope, quantity x minus x1. Remember, x1 and y1 are the ordered pair values in this case, so just put them in their appropriate spots. Notice we're going to have a double negative situation here on the left side. And for the purpose of the AP Calculus exam, you could leave your answer like that. There's no need to go any further with it if you have a free response question. I often tell my students not to go any further because you could potentially lose points if you did that. But as a multiple choice option, you might see a few things simplified in the course of maybe getting y completely by itself. So you just want to be real careful with problems like that. For the purpose of this demonstration, this video, I'm going to call the answer there. So that leaves us with part E. Write the above equation, rather, explicitly. And we're going to use our TI graphing calculator to verify the graph from part A. And we're going to also take this derivative explicitly, and we'll compare that result with the one that we got from part B. So we first of all have to think about, what does it mean to write an equation explicitly? Well, that means basically to get the independent variable on one side and the dependent variable y all by itself. So we'll start by subtracting x squared, then we'll divide by 4, and then we notice that y is not quite by itself yet, so we could think about taking the square root of both sides of this equation. That will certainly give us y on the left side. Now on the right side, what you're about to see can get a little tricky. A lot of times students forget whenever you square root both sides of an equation, you have to consider the sort of birth of two different answers because a negative value squared will end up being a positive value, of course, and we always just put this plus or minus in front. And we could do a little bit more to this to simplify it. I definitely advise this because we are going to have to take the derivative of this. Cleaner the derivative, the better. So we're going to basically take the square root of 4, which is in the bottom, which would be a 2, of course, and if we factor that out, it'll look as if it were a 1/2 out in front of the square root. And I think we've got ourselves in a pretty nice position here. Now, to take the graphing calculator and to verify the graph from part A, you would have to enter this function a little bit unusually into your calculator. And I'm not going to actually show you on the calculator per se, but to give you an idea, you would have to use two entry lines, Y1 and Y2, say if you're a TI-83 or 84 user, or F1 of X or F2 of X if you're a TI Inspire user. And you'll notice that if you use the positive version of this result, it'll graph the top half of the ellipse, and the negative version of that result would graph the bottom half of the ellipse, and the two would seem to kind of fit together seamlessly. And that's really the old school way to do this. Back when we were just using TI-83s and 84s, we didn't have much of a choice but to graph these as such. The Inspire definitely makes it a little nicer. So we look at our next thing that we need to do, and that's to take this derivative explicitly. And then hopefully we'll get the same answer as we did in part B. So if we take a look at this y equation, it doesn't quite look like it's 100% derivative ready, but we could think of that square root as being a value, like a fractional exponent of 1/2. So we'll write it like that first. I think that might be wise. Now you got to think about your strategy here in which you want to use to take this derivative. Plus or minus drop straight down. We're going to multiply the 1/2 and the 1/2 to get 1/4. And then we've got the contents within the parentheses, 4 minus x squared raised to the negative 1/2. But the chain rule is going to be active here because we take the derivative of what's inside the parentheses to get negative 2x. Derivative of what 4 minus x squared would be. That would be our negative 2x. Now, it could be cleaned up a little bit. This doesn't quite look anything like our part B. So I could maybe combine my 1/4 and my 2 to get a 1/2. And I'll throw the x in there. And then I've got, essentially I could rewrite this 4 minus x squared to the negative 1/2 as 1 over radical 4 minus x squared. But you'll notice that you still don't see the same answer. And this negative sign, that negative sign is kind of interesting. We don't seem to have accounted for it just yet. And you've got to remember that this was part of this dy dx. I don't think it's wise to manifest the negative out in front and maybe change the plus or minus to a minus plus. Some kids want to do that. Let's go ahead and just make a negative sign appear like I did with that 1 on top. So what I'll do now is I'll just rewrite this so that the x also appears on top. The 2 will sit alongside the square root in the bottom there. So this is what I've got for my dy dx. Now, remember this guy? Pasted him in again. That was our answer from part B that we've been using a little bit throughout the problem. Notice these don't look very much alike. Well, we still have one more thing that we can do to try to get them to look alike. And that was sort of the directive here in this part E. So you think about this a little bit and you think, what is different about these two things? What I've written there in black versus the boxed in blue. Well, it seems like that denominator is a bit different. 4y seems to have the same value as that 2 radical 4 minus x squared. So what we're going to do is just kind of manipulate a little bit more with this. And what I've done here is I've kind of revisited the original y by itself expression that I had up there on top. And think about that a little bit. That's what our y was. So if we were to sort of find a way to make this 2 radical 4 minus x squared contain this y value, what we could do, I guess there's a lot of things that we could do, but I think the easiest thing would be to do this. Factoring out that radical 4, if we recall, that radical 4 in the denominator comes out to the front, and then all of a sudden you see that the denominator is going to be a little bit closer. But we have this 2 and this 1/2 that seem to be a little bit in conflict. So what if we were to multiply our y by a 4? Well, we would go ahead and find 4 times 1/2 to be the 2, and then our square root of 4 minus x squared just plops right in. And now you will notice that looks very familiar. What I've got circled here compares very nicely with what I've got in the denominator. And moreover, it also includes that plus or minus symbol that was left out in front. It's kind of tricky to do the comparisons here in Part E, but I always like to show this to students just to make sure that it is true that implicit differentiation does work. It is a lot easier to pull off than this derivative here that we did in Part E, and never would I have students take a derivative explicitly if they didn't have to, because this answer in the blue box works perfectly fine, and it's okay to have an answer in terms of x and y. Anyway,